being the remainder theorem of a geometric series, in which we are going to use to find the value of n, or the lowest integer value of n, in order to approximate the proper error of a geometric series within 0.001. I'm going to start with the proof in this video. So then, first things first, we're going to write this out as this nth partial sum of a geometric series. Then we're going to multiply times r, and we're going to stack both of these equations and subtract. And just out of convenience, when we stack these, we can cross cancel, of course, because you are subtracting those terms. And so if we multiply these, if we go ahead and split up our common denominator here, 1 minus r, we will pull out an actual s, um, respectively, for the infinite sum. And then, of course, what we have for our remainder formula from this expression. So quite conveniently, if we plug back in our actual definitions, we'll arrive at this any way we can assort these to get any calculation that we're looking for. And the remainder in the geometric series, in the sense that you've got s minus a certain amount of n partial sums, is by definition the error. So again, you will have by definition these sums, the total sum, the remainder formulas that we're so accustomed to, and the nth partial sum. And you can sort them for whatever question you've been given. And the remainder, again, is the error. So that would be this term right here. So here's an actual example where we have to find the exact sum s of the geometric series. And I'm going to use the error theorem here, remainder error theorem. We are looking for the error to be less than 0.001 in this example. So we will set it up like this, where we have our remainder reorganized from what we had last time. Of course, you could resolve for this and have s minus Sn. Kind of useful knowing how to rederive that formula for the error of a geometric series. I usually like to be extra cautious and go ahead and kind of see what my sequences are doing. You don't have to go too far out. So earlier on, I didn't note that a is just a factor in this case, just a scalar. You don't have to be. If you have a different a in your example, then you would go ahead and use that respectfully. So then we're going to go ahead and like I said, I'm going to use this table. And if you have a different value for a, well, then we'll go ahead and use that in our formula. So then what we'll get when we rearrange our terms here from what we proved earlier for the remainder is we'll just see that a part of the nth partial sums in S will cancel, or you can just use what we get from the actual remainder identified in this step. So it's really nice. You can do it multiple ways. I'm just justifying it here, but all you really have to do is pull from that formula. Just don't put the negative sign there if you're just going to extract it over here. So these two are going to cancel, and we're going to be left with what we need to use, or what formula we need to use to find a remainder here. So in this case, for our ratio, we discovered that that was 3/7, so we're going to go ahead and plug that in. And so just plugging in that information now for the remainder, remainder formula here, we're going to get this. But we need this to be less than the error being 0.001, albeit the remainder, respectively. So next, we're just going to take the natural log of both sides and absorb that 1 over 10,000 in the denominator. That way we can drop our n plus 1 using log properties. Okay, in this situation, just kind of proving that these were justifiable by dividing by that negative number. You do get a positive number from that, 8.8 and some change here. You subtract 1, you get 7.8. But if you want greater accuracy, if you want to ensure that it's within 0.001, it would be logical just to round us to a whole integer value, which we have to have for the series. So you would round up because the more terms you have, the more accurate your series converges to the function that we're dealing with here, this geometric series. So we would say anything for n greater than 8. So here we need to understand that even though our common ratio needed to be beneath 1 in all of this, and we're setting this up, um, it's you would use logic, and you have to understand that it would be greater than or equal to, of course, because you are trying to find that exact value to get the error within 0.001 for this. In other words, it would need to be greater than or equal to 8. We would round up to ensure greater accuracy because we can't use 7.81. And again, we are invoking the greater than or equal to sign, as n would be an exact whole number integer value. And this would be the lowest we can go for n to ensure that accuracy within an error of 0.001.
Yeah, coming! Let me hear 'em coming! Come on, come on!